Recording. Cool. All right, it's my pleasure to welcome Joy Harris. She's an undergrad here. She'll talk today about independence polynomials of two-step nilpotent algebras.
All right, thank you. You guys can probably tell I have a bit of a cold, so I'm sorry. But yeah, this was the REU project I did with Virginia Commonwealth University over the summer. And so I still have the two people that I worked with, Thor Gabrielson and Cal Kelly, as well as the mentors that I worked with, Dr. Aldi and Dr. Grandini. They obviously, this project was a group work. And so what it is that I'm presenting today was the work of a lot of people. But to kind of outline what this talk is going to be about. So the first bit of this is just going to be kind of preliminaries to make sure that everybody is all on the same page about both graph theory as well as some Lie algebra stuff. Then I'm going to move on to some of the earlier results in the project. And then moving into talking about some bounds on what's going to end up being the single variable independence polynomial. And then going into sort of what ended up being the main result of this project, which was the bivariate independence polynomial. So to start, I'm going to just quickly talk about graphs. I'm sure that most people have seen graphs, but just in case you haven't, a graph is the set of vertices as well as a set of edges, where an edge is just a set of two vertices, where you have your vertices, have your edges. And these are the sets that define the graph that I have here. Graph independence. So an independent set, it is a subset of the vertices where no two of the vertices are connected by an edge. So the green vertices here, this is an independent set. It's of size 4. And the number of independent sets of a certain size is denoted by GK, where K is the number of vertices. And obviously, it's kind of interesting. What is the biggest independent set in a graph? And so this is given by the independence number. It's the largest K where there's still an independent set. And if you want to think about all the independent sets of sort of all the sizes, you look at the independence polynomial, which has all that information sort of encoded in there, where the exponent of your variable tells you the size of the set and the coefficient, how many sets of those sizes are independent. Finding out this independence polynomial or the independence number, it is NP hard. It's not easy to do. And so that's why I'm kind of moving on. You kind of want to focus more on finding bounds on this rather than finding the actual number. Just quickly, because this is going to become important a little bit later in the presentation, a hypergraph, specifically a K-uniform hypergraph, it's a kind of a generalization of a graph where rather than edges being a set of two vertices, they are a set of K vertices, but all of the edges are going to have the same number of vertices. So here, all these edges, on the one on the left, they have 3. All the ones on the right, they have 4. All of them are going to have the same number of vertices, but it's more than 2, usually. So now that we've kind of gotten graphs out of the way, I know that many people here are much more experienced in Lie algebras, especially that I was at the beginning of this project. But this is the definition of Lie algebras that we used when we were doing this project. It served us fine, where a Lie algebra, we're going to define it as just a vector space that has this operation called brackets, where we're just going to bracket two things together. It's going to give you another element of the Lie algebra. And it has to follow these 3 properties, where it's bilinear. You bracket something with itself and it's 0. And it has to follow the Jacobi identity, which is that long thing at the bottom. And it's because of these that we have anti-commutativity with the brackets, which did end up being pretty helpful throughout our project. Some examples of Lie algebras. I'm sure that many people have seen the cross product over R3. But this example is sort of upper triangular matrices, but nothing on the main diagonal. This is a special algebra called a Heisenberg Lie algebra. They show up in quantum mechanics. They do have a physics kind of derivation where, this is a real thing, not just something that mathematicians made up because they thought it was cool. But this kind of special Lie algebra is something that we focused on a lot. As you're going to see later on in this presentation, the exact reason as to why. But now that we have graphs and Lie algebras, we kind of have these two separate things. We kind of want to try to bring them together so that we can analyze them both. And so that's where the Dani-Mainkar construction comes in. So if we take a finite simple graph, so no edge colorings, nothing fancy, we can actually make it into a Lie algebra. So we kind of take the vertices and edges; those are going to become our basis for the Lie algebra, and we can define the bracket operation that I mentioned earlier, where the y's are your vertices, and you bracket two vertices together, and they will give you the edge that connects them. And because of the anti-commutativity property, there is an ordering of it where there is a sort of like negative edge where if you bracket them in the opposite order. And by this theorem by Mainkar, we actually have that Lie algebras that we get from these graphs, they're isomorphic if and only if the graphs themselves are isomorphic. So this connection that we get from these graphs to these Lie algebras, this is a sort of a very potent connection. So as a kind of example of what exactly one of these constructions would look like, we can take a very simple graph, just a path on 3 vertices. And we can get this sort of construction where you can bracket 1 and 2, or you can bracket 2 and 1, you would get that edge, or you would get that edge backwards, depending on which order you did it in. But we also note that if you try to bracket anything else other than what you see above, like you try to bracket one of the edges with something, you're going to get 0. So this is just an example of what that construction would look like. The DDMR construction is sort of, it stands for DeCoste-DeMayer-Mainkar-Ray, the people who came up with this. This is a little bit more sort of like, I guess, a generalization where rather than just a simple graph, we can now actually do things with edge colorings. So rather than y1, y2 evaluates to the edge, it might evaluate to the color red, which it might share with many other vertices or edges. Like here, we have a graph where there's 2 red edges. And so the brackets evaluate to the color rather than to something specifically defined by those vertices. And this sort of opens up a lot more interesting things, especially when we start actually sort of getting into some like differentials and stuff on this. The Lie algebras that we're going to be getting from these constructions, they're going to be two-step nilpotent or metabelian. That basically means if you bracket something, you bracket the vertices, you get the edges, but you try to bracket again, then you're going to get nothing. So it only takes 2 steps before your bracketing kind of gets you to 0. So, like I said earlier, that Heisenberg Lie algebras were especially of interest to us. And part of the reason why is because they can actually be pretty easily kind of manifested from the DDMR construction, because you could think of them as n disjoint paths where every single edge is the same color. So something like this would be a way to sort of visualize Heisenberg Lie algebra outside of the matrix definition that I gave a little while ago. So moving on to something that is very important and was very important in our project, and is also going to be a very simple definition compared to what many people use, but this is sort of the very just basic definition that we use for our project, was that for a basic cohomology, we're going to be splitting up the basis into our y's and our z's. And we're going to define the differential where if you try to plug in any y, it's going to give you 0. But if you plug in z's, it's going to give you a linear combination of the y's that bracket to it. So that means if you put in z, which was the edge between y1 and y2, this would then give you 1 and 2. And we can define the basic cohomology using this differential. And it's going to end up, this is the basic cohomology, which means that we don't want any z terms at the top. We just want them to be y's. And that's why we're only going to have the polynomials from y1 to yn is going to be degree k, because this is k kind of basic cohomology. And then we're kind of modding out by the image of D on polynomials of degree k minus 1, but they're going to have like what's going to end up being 1 z term in there. So,
sorry, can you go back?
Yeah.
In your formula where it's the bracket of yi, yj equals this stuff, should that be zp?
For the C? Or,
Okay.
The like, it's ZK, but I think there's no K. I think maybe we want it to be P, is that right?
Then the formula on the
Mhm, I see. Yeah, probably. I believe that was probably just a typo, me putting in the wrong letter.
Yeah, it's fine, I just wanna make sure I'm,
Yeah, no,
No.
thank you
You're wrong.
thank you for stopping me. Yeah, but now that we've got the definition, sort of all the things that we need to like start, this is where we kind of started working on things. We can get sort of our first most basic results. The first one is specifically being relating the dimension of the kth basic homology with the number of independent sets of size k. So this is kind of what's going to start really building our connection between Lie algebras and graphs. So we're going to get the dimension of the kth degree basic homology on the Lie algebra that we take from a graph. That's going to be equal to the number of independent sets of size k from that original graph. And so kind of the idea behind this is if we just kind of like sort of count to the number of polynomials we have on the top versus the number of polynomials we have on the bottom. The polynomials on the top are going to be sets of the y variables, and the polynomials on the bottom are going to be sets of the y variables with an edge. But since they have to have that dz term in there, that means that everything on the bottom is going to 100% like guaranteed contain like a yi, yj with an edge between it. So that means that all of the polynomials on the bottom, they represent sets of the y's, subsets of the vertices that have at least one edge. So that means we're taking all of the subsets of the vertices and then modding out by subsets of the vertices contain at least an edge, which leaves you with the subsets of vertices that don't have any edges, which is the dimension of that would be the number of independent sets of size k. The next result, oh yeah, well, that's why we define the independence polynomial for a general Lie algebra in terms of the dimension of the basic homology, the kth degree basic homology, which this is actually going to let us get independence polynomials of Lie algebras that do not come from graphs, because now this definition doesn't directly depend on being from a graph. So the next result, sort of in this early era, was the dimension of the kth degree basic homology for Heisenberg Lie algebras. And this is again another counting argument. The 2 to the n choose k, or 2n choose k. That is just a number of polynomials in y, 2n y variables. You pick k of them. That'll give you your polynomials in y. And your polynomials on the bottom, since you only have one z term, you just pick k minus 2 other y terms, and that'll give you your polynomials on the bottom. And it turns out both of these sets are linearly independent. And so that's why this is an equal rather than a less than or equal. So this relationship holds all the way up to n, where after n, this is going to be equal to 0.
So I think I missed something. So what does it mean when you have the HK without the B?
Oh, right, the HK without the B, we didn't really use the non-basic homology very much, but that it ends up being as well that the basic homology is actually equal to the non-basic homology.
What do you mean by the non-basic?
Where you're allowed to put z terms sort of in the top. For the basic homology, we took the z terms out. And so the result on the left says it like, even if you put the z terms in, it doesn't actually change the dimension. Right, so after this, we kind of left the period of some of our earlier results, and we started up thinking about like, okay, we now have this way to define independence polynomials for Lie algebras that don't come from graphs. And so do the properties from graph theory still hold for these independence polynomials? And specifically, do the bounds still hold, since the bounds are the things that we calculate in polynomial time. So they're interesting, and we want to know if they're still actually valid. And so 2 of the bounds that we looked at for simple graphs were the Hansen upper bound and the Taran lower bound. And we can translate these bounds, sort of taking the number of vertices, number of edges, translating that into Lie algebra language, where the dimension of the first degree basic homology, like that's basically just all of your y variables, your degree 1 polynomials. So that's why that's the number of vertices. And the degree of the dimension of the Lie algebra minus all the vertices, that's the number of edges. So now that we have a way to translate the bounds, do they actually hold? And the Hansen upper bound does. I don't have the proof for you here because it's a little complicated, but the part that I was more involved in was finding that the Tehran lower bound did not hold. Because there's a counterexample that you can see here where the Tehran lower bound estimated something greater than 3 when the independence number was exactly 3. So if the Tehran lower bound doesn't hold for these Lie algebras, we want to find something that does. And so this is the bound that we ended up coming up with. And the B1G is just sort of shorthand. You can think of it as the number of vertices. So the way that we got this bound, it's more of the counting argument, or counting number of terms on the top and number of terms on the bottom. Duplicated. Yeah. So if we look at an example, we have here where we're trying to count the number of terms on the bottom and the number of terms on the top. If we're looking at like a really small example, so just like Heisenberg, two edges, that means if we're looking at the second degree cohomology, we're looking at polynomials of degree 2. We have 4 vertices to choose from. We're going to get those 6 polynomials. And the only polynomial on the bottom is going to be this one, the one that we get from Z. And so it's going to be clear we have 6 polynomials on the top, 1 polynomial on the bottom, and we also are going to have that that each of the ones on the bottom will only be able to take off 1 from the top because none of them are going to be kind of in the same like equivalency class in that way. So that means that there's no way that this is going to be 0, since there's going to be stuff on the top that it's not being modded out. So that means that if we actually want this to be 0, we have to have at least as many monomials in the bottom as we have on the top. So the number of monomials on the top is just given by the number of y, like polynomials in y that we can make given the degree. And the number of polynomials in the bottom is the number of polynomials in y of degree k minus 2. But for each one of those polynomials, we can multiply it by any of the z terms, because there could be multiple, maybe, there's multiple colors or there's multiple edges. And so that means that's why we multiply that number by z. And we can translate these numbers sort of back into Lie algebra terms in order to get the bound that you saw earlier, where the B1G is just, the number of y variables you have to pick from. And the dimension G minus B1, that's just Z times the number of variables you have to pick from, choose K minus 2. So alpha G plus 1, this is the first number where it's even possible for us to have enough monomials in the bottom to cancel out the top, which means that alpha of G does not have enough equations in the bottom. So it can't cancel out everything on top, which means it has to be non-zero. This is what's going to give us our lower bound. So we found a lower bound. Is it actually good? In terms of simple graphs, no. Algebra we did some math, and it says that Tehran is always like greater than or equal to ours. So no, is it useless? But thankfully also no. It seems to be useful for hypergraphs. So this is kind of where we took a detour into hypergraph land, where we can now translate our Lie algebra bound into hypergraph language, number of vertices, number of edges like we had. And we can start trying to compare this to the hypergraph bounds that already exist. So the Tehran lower bound for hypergraphs, which is different than the one for graphs, for simple graphs. Since both bounds are determined only by the number of vertices and number of edges, that's why this graph is like so nice and clean, because you can just calculate what combination of edges and vertices that were better. And these dark gray bands show you those combinations. So it's clear that there is, in fact, some area where we found something that is somewhat useful. The shaded area, the striped one, those are impossible graphs. Those can't exist. Another bound for hypergraphs is the Karatuzza bound. this bound is actually calculated using the degree of vertices of the graph. So this isn't something that you can calculate so easily for whatever combination you want. That's why this was sampled, but you can still kind of see those dark gray bands, patterns where, for at least the ones that we sampled, our bound ended up performing strictly better than the Cartesian bound. But after this, we kind of left the stuff that we did with bounds, the stuff that we did with hypergraphs, and we went back to
Wait, sorry, I can ask a question.
yeah.
So I guess I understood the construction of these Lie algebras starting from a graph.
Mm-hmm,
But now you're kind of applying this to the hypergraph setting.
mm-hmm.
What is how am I actually like taking my hypergraph and cooking up a Lie algebra from it?
Yeah, so what we ended up doing was we took like the bound that we made and then just reproved it for hypergraphs using just hypergraphs, though it's the same, it was sort of a similar idea and ended up giving us what can be kind of translated as to being the same thing. And you can actually do like Lie algebra stuff with hypergraphs, so we didn't do as much of that in the project. This was kind of us stumbling upon this bound and just trying to find somewhere that it could be useful.
Great.
So that's why kind of after we twiddled around with this, we're like, wait, this is the Lie algebra group. So we kind of got back to working it with Lie algebras, and this is where we're going to start defining the bivariate polynomial, which is where our main result is going to be coming from. So if we can recall the derivative or the differential that was defined earlier, we're going to define a new operator, the adjoint operator, which we kind of thought of as like the antiderivative the entire time, where instead of putting in z's and getting the y's that bracket to it, now you put in two y's and it gets you the z's that it bracket to. And so if we want to see these operators in action, we can put it through this this polynomial, which is from the Heisenberg two lines, and you can see that since y1, y2 is a line, it'll end up bracketing to that z when you put it in through d star. And same thing with y3 and y4, it'll end up bracketing that z. We're gonna have a linear combination of them both. Now that we have these two operators, we are going to define the basic Laplacian, which is sort of d composed with d star composed with d. And we're only going to be plugging in the vertex polynomials. That's why it's the basic Laplacian. We're not plugging in any z's into here. And it's because we're not plugging in any z's into here that the d star d term doesn't actually end up being anything. Because if the only things that end up being non-zero when you plug it into d, they have to be z terms. And since we're only plugging in y's, that's going to be 0. So this is we have now kind of defined the basic Laplacian, which we're going to be using to then try to get our bivariate polynomial. And so the way that we sort of, I guess, derived it is from, we take the partition function. This comes from physics and thermodynamics, so the actual details of it, I was not, we weren't really privy to. And it can be generalized also, physics, thermodynamics, into what we ended up using, which is this bottom one, given by the trace of S raised to that basic Laplacian, and then T raised to this matrix F. So we need to show the Laplacian kind of as a matrix in order to be actually able to do this matrix exponentiation, and also just what is this F matrix that we have made. So we're just gonna turn like the Laplacian into kind of just like any other linear transformation, where you can turn it into a matrix where you kind of have the basis, which are going to be our vertex polynomials that are in Y. And so you plug in your Y's, what's the linear combination that the polynomial is going to come out as, that's what your matrix is going to be defined by. That's when we're going to be able to actually do the matrix exponentiation, which is defined by the Taylor series and F. The F matrix, we're just using that to sort of keep track of the degrees of the polynomial. So it's just a diagonal matrix that has the degree of the Y polynomial sort of encoded in it. So what does this actually mean? We've defined this sort of polynomial, but does it actually mean anything, especially in regards to sort of graphs? If we take the simple graphs, so not from the DeCoste-DeMayer construction, just the Dani-Mainkar sort of graphs, we find that it's going to give us this polynomial, which it's almost like the independence polynomial. In fact, if you plug in, if you say like, oh, I'm going to let s equal 0, I don't want the s term, this is the independence polynomial. Because what this is it's t raised to the size of some subset of the vertices. And your s term is the number of edges in that subset of the vertices. So rather, in the independence polynomial, it would just say, okay, this is how many subsets have no edges. But now this polynomial, maybe the s term or the s squared term would say, this is how many sets have one edge in them of size, whatever, how many have two. And so this is a version of the independence polynomial that comes with a little bit more information. But why does this actually work out? Why does the basic Laplacian kind of give us this sort of really nice sort of independence-y polynomial? And so I'm just gonna kind of work through an example so that we can kind of see how it is that it's defined this way. So if we just take like a simple square and then just look at the polynomial, which is going to kind of equate to the subset of 1, 2, 3. And we're going to apply the basic Laplacian to it. And when you do that, you're going to end up getting 2 of the polynomial that you started with. And so that means that this is just going to be 2 on the main diagonal. And this is actually going to hold for every single polynomial that you plug into this, where you're just going to get multiples of the polynomial you put in, and the coefficient, that multiple, that is the number of edges or in that set. Where you see the set 1, 2, 3, it has 2 edges. That's why our coefficient was 2. And so that's why our s term, which is determined by delta b, which is a diagonal matrix that just has the number of edges in each polynomial. The s term, that's why it corresponds to just the number of edges in each polynomial. And t is the coefficient of that. That's determined by the degree of this polynomial. And as you can see, y1, y2, y3, degree 3, it corresponds to the subset that has size 3. So that's how that we kind of see that, like, okay, this sort of bivariate polynomial actually does mean something for simple graphs. So does it mean something for maybe if we put an edge coloring on it, or maybe if we put in a Lie algebra that doesn't come from a graph at all? But like if we take this one, this really doesn't look that bad. It's got like 7, 8 elements to it. It looks like that. And it gives you really weird irrational exponents, which it doesn't seem to make sense with the interpretation from before. So these are hard to calculate, and also hard to look at. So we maybe want to see like, okay, well, maybe not in general, but in a special case, get a formula for one of these things. And so we turn back to our old faithful special case, looking back at Heisenberg Lie algebras. So we want the delta b. We end up finding that for the Heisenberg, the delta b, this is actually going to be a block, like a block matrix. So that means that it's not going to be as bad to exponentiate. It's still pretty bad because matrix exponentiation is pretty hard, but what actually makes it even simpler is that the blocks of these matrices are actually given by a specific graph, a Johnson graph, plus some extra stuff. But why exactly does this happen? First, just like what even is a Johnson graph, because it's not something I'm sure that everybody knows. A Johnson graph is specified by 2 integers, n and k, and the vertices are k element subsets of an n element set. So here, you can pick from 1 through 4, but so n is 4, but each subset, each vertex is a subset of 2. And the vertices are connected if their intersection is size k minus 1. So in this graph, you'll have that if sort of in the top where 1, 2, and 1, 3 are connected, 1 is their intersection is size 1, so they're connected. But that still doesn't answer the question. Oh, no.
You can always splice the thing. You better. I don't want anyone to. Change the. We can get them in. We'll just have her start at. the Slide.
Yep.
B.
Have her, want her back up one and then we'll slice it. So.
Okay, back up one and just sort of,
Yeah, and then just start with that.
yeah.
Okay, go ahead.
Okay, so, yeah, since their intersection is size 1, they're connected by an edge. So, why does this actually like give us anything? So it's like, cool, we know what a Johnson graph is. I don't see how that's connected with the Heisenberg Lie algebra. So this is sort of just trying to get the intuition as to why exactly this happens. So we sort of broke up, since Heisenberg Lie algebra is very, very nice, sort of very simple. We can kind of split our polynomials into we can think about pairs, loners, and then just trying to keep in mind the number of edges we have. This is a bad drawing because I'm not good at text pictures. But this is a Heisenberg Lie algebra. Let's just take the polynomial, just y1, y2, y3. And we can see that if we're just going by pairs, you know, y1, y2, they make a pair since they're connected. It has one loner, y3 doesn't have its buddy, y4. And so when we do the Laplacian, do delta B on that, you know, it's not going to be as nice as before, where we're going to get a nice diagonal matrix. But what we do end up having is that we're going to get a copy of what we put in, but we're also going to get another polynomial where our pair has been replaced by another pair. It's been replaced by 5, 6. And so what delta B was going to do is it's going to take pairs and then turn them into other pairs. It's also going to leave all the loners fixed. So another thing that delta B is going to do, it's not going to change multiple pairs at once. So if this was like a y1, y2, y3, y4, y5, delta B wouldn't immediately you wouldn't be getting I don't know, I don't have enough elements, but it wouldn't change the pairs 2 at a time. It only changes them 1 at a time. So what we can kind of think of this as we're mapping like a polynomial to a linear combination of the other y polynomials through delta B. And they all have to share pretty much everything except for one pair, since one pair is being changed at a time, which means that if the intersection is going to be the number of pairs, sort of -1, because all the pairs are the same except for 1. Now we can kind of see where this is getting into the Johnson graph, where they're all the same except for that one difference. And we have that k minus n term, right? So where does the number of loners, the sort of that y3 hang out by himself? Why is he important? And like I said, loners have to stay fixed by delta B, and that actually restricts the edges that you can map to. Delta B cannot map 1, 2 to 3, 4, since that the y3s would then multiply and cancel each other out. And so the loners kind of end up restricting what pairs that we can map the pairs of y to. So that means the number of available edges that we can map a pair to is k minus n. Also, just the last thing, like I said, in the last example, because of the mapping returned the original pair. This is going to happen no matter what pair that you map your pair to. So that means if you have n pairs and you're trying to map them to m things, you're going to end up with m copies of the original. So that's why for in delta B, we're going to have m along the main diagonal, which is presented by this m times the identity, since you get m copies of the original. So this ends up being our formula for the blocks, given by the Johnson graph adjacency matrix plus the m times the identity. So we can use this as well as some other sort of tools that we have, where because mi kind of commutes with everything, we can then break up that exponent and Since adjacency matrices are symmetric, we can diagonalize, which means that we can turn our matrix into a diagonal matrix, which is great for exponentiating. And then we can even take those p's out of the exponent. So with all that, we can actually simplify that bivariate polynomial that we started with, which was kind of nasty, is something that looks a lot better. That's going to be much easier to exponentiate because we now have a diagonal rather than having sort of the mess that we have. But diagonalizing still is very computationally expensive. So is there any way that maybe we could just write down some formula rather than having to do it from here? Well, we know that if you diagonalize something, the things on the diagonal, that's going to be your eigenvalues. And the eigenvalues of Johnson adjacency matrices are actually, they are well known, published in this paper or in this book, given by this sort of nasty-ish looking equation. So that means that we now have sort of a formula for the powers of S. And, we have to add the M because of the MI. This book also tells us the multiplicities of the eigenvalues. And if you have an eigenvalue show up more than once, they're going to end up adding together, which is just going to end up being your coefficient of this term. Another thing that we're going to have to look out for is that some of these Johnson adjacency matrix blocks are actually going to appear they're going to appear like multiple times because they have to fill out the entirety of delta B. So we have to count how many times are these going to show up. So if we end up putting all that together, I will explain what all of the parts are. But we actually can get a formula for the bivariate independence polynomial for Heisenberg Lie algebras, sort of using all of these parts. So just explaining what everything is. So this term up here, this is the number of blocks that we're going to end up having, where this number at the bottom is it's an n by n matrix, so it's like both the length, width, height of the Johnson adjacency matrix, and this is the number of polynomials that have m pairs and n loners. And so since all the polynomials with m pairs and loners are going to have the same Johnson adjacency matrix, that's why we're going to have that many copies of the same one. And the sort of choose minus choose statement, that is the multiplicity of the eigenvalue given in the book. So with that, like we also have S raised to that's the eigenvalues, and T is just raised to the degree of the polynomial, which is 2 times the number of pairs, since each pair has 2 y's in it, and then plus the number of loners. So with that, we have found a formula to kind of describe this polynomial, which had once seemed so enigmatic. And with that, would like to thank the NSF for sponsoring this work, as well as Dr. Hubbard and Dr. Larson for graph theorists who basically told us stuff about graph theory we didn't know. And then, of course, thank you to Dr. Aldi Grandini for being so nice during this for you. Thank you.
At the end, you worked on this nice story for the Heisenberg, the algebra, or the graph associated to it, and then you, from that, you kind of found this Johnson graph, sort of associated to that. If you replace the Heisenberg algebra by something else, maybe not a totally general thing, but are there other nice families of graphs like these Johnson graphs that you can get by taking some sort of different version of the Heisenberg?
I mean, that would be a really interesting question to explore. We kind of discovered the Heisenberg stuff 3 days before the REU ended. So as much as we wanted to try to find something like that, we would really like to, but this is sort of where we ended up at with the time that we had.
So in reference 7, you sort of mentioned, it says cohomology of Heisenberg Lie algebras. Is this like the ordinary Lie algebra cohomology or is it something else?
I don't think, I don't know. I don't think I personally drew from that one. So I honestly don't know what's in there.
So is, when you talk about the cohomology, I mean, is it related to the ordinary Lie algebra cohomology or isn't it ordinary Lie algebra cohomology?
I'm not entirely sure. The definition that we
I think
presented
it
was.
is. I was thinking about it a little bit. I think it is. I'm not entirely sure, but it's like some explicit
Yeah,
realization of it. I think so.
I think so too. But, yeah,
I'm not sure. I mean, it seems like it should agree in this specific case, but I can't say for certain.
right, because I was thinking of that degree 2 example here. I think it does.
Yeah.
Okay, good. All right. I think we answered the questions.
There are no further questions, like, let's thank the speaker again.
We are going to try.
Thanks.
If you email me, I already gave it to them. If you didn't, and if you want to come, just let me know.